I'm your presenter for this session, Divyam, and I'm the Systems and Interface Lead for the Western Solar Car team. Now, to start off with, I really want to quickly give an overview of what this session is going to encompass. The purpose of this presentation is to really showcase the ways in which the team uses various forms of simulation technologies to create a lighter, safer, and cheaper solar car. We want to share the amazing capabilities of these software, some really exciting features it offers, and why skills in this area should appeal to any business or engineering professional. I also want to let you know that a lot of the geometry or simulation data in this presentation is not representative of the actual solar car components, but more of some demo images. And now this won't be a tutorial on how to use the software or such, but I'm happy to help more if anyone does want to reach out afterwards with questions. So the first thing I want to sort of go through is FEA, or Finite Element Analysis, which is a way to computationally simulate the mechanical stresses and strains going through a part in response to some input loads. Almost all mechanical parts of our solar car are designed in-house. This allows us to optimize the parts to be as light as possible for its given loading case. However, we can only get so far based on first principles and intuition. To produce a highly efficient and safe machine, we employ FEA to analyze each and every mechanical component that we design. The team uses the ANSYS software package to do this. However, there are many different products available. The general process of performing an FEA analysis is to design a part in a CAD package. The output of this CAD can be imported into ANSYS. Within ANSYS, we first need to mesh the part, which I'll go into more detail about later in the presentation. Next, you can specify the material that the part is made out of, the load points and types, the support points and types, and what results you want out of the simulation. It supports simulating direct loads, distributed loads, remote loads, pressure forces, moments, and many, many more. Additionally, you can also simulate different support joints like fixed, pin, roller, etc. Based on these conditions, the simulation results can output various different parameters that describe the behavior of the part. The main ones we look at would be the stress distribution and strain, deformation, and factor of safety outputs. Now, the amazing part of this software is that it is displayed as a 3D color graph that's overlaid on the part itself. This allows a more visual understanding of weak points and over-engineered sections. Using this, you can add material where it's needed and remove it where it's not. Now, bear in mind that this is a very simplified explanation of the process. We use FEA to iterate our design multiple times until we are pleased that it is up to our safety standards and as light as possible. And through, tight engineering management, we are able to get our factor of safeties, to be just within a high performance envelope, so we can get a light car that is also very safe. Now, simulating individual components is quite useful. However, it doesn't always show an accurate picture. Using ANSYS, we also have the ability to perform FEA analysis for entire systems that contain those components. Here, we can set various contact conditions that define the interaction between various components as shown on the screen. Now, for example, the contact surfaces of a spherical joint can be set as frictionless, and this allows it to rotate freely, but not come out of its housing. It's important to note that this type of FEA is still on a purely rigid body with no mechanical movement designed in, but setting appropriate conditions is very, very important. In this example, setting the spherical at the bottom to be movable doesn't let the upright turn, but it does ensure that all of the moment loads that could be applied to the upright is counteracted by the shock joint and not by the lower control arm. And in this way, it gets closer to the real world outputs the real world conditions that this would be under. Full assembly simulations account for all of internal interactions, as well as the adding up of deflections throughout the assembly, overall providing a much more accurate understanding of how the parts are behaving. Another great tie into the FEA process is the ANSYS ACP tool. What this allows is a simulation of parts that are manufactured out of composite materials. A very large portion of the solar car chassis is made out of composites, so this allows us to perform FEA and to optimize it. The ACP method involves the design starting as surfaces and not as solids as before. Onto the various faces of these surface bodies, you can specify the layup schedule of your composite that you have in mind. We can define the type of composite, the number of layers, the angles of each layer, any core material, as well as any glue films, and etc. using ACP. It also allows you to specify any relief cuts, which are often areas of concern and can be quite harmful if not designed appropriately. After specifying the composite makeup, you can perform the normal FEA analysis procedure, but you can view additional solution parameters regarding composite-specific failure modes. The ACP toolbox is instrumental in the design of the solar car and can prove useful for any composite design process. The last thing I want to discuss about FEA are the extensive special features that programs like ANSYS enable. Within the FEA workflow, you can specify things like bolts and their pretensions, glue joints, weld joints, and all in all, this increases its accuracy and versatility drastically. ANSYS also offers two amazing optimization options that allow you to take your design to the next level. One is called direct optimization. In this, you make the part itself parametric. So for example, if you want to imagine a large flat panel that is supported on the bottom by various bars, through direct optimization, you can set the thickness, depth, and the material of these bars as parameters and not as fixed variables. Through a direct optimization loop, you can set a constraint like, let's say, a minimum factor of safety of X, and a target like minimize weight. And let ANSYS automatically perform various simulations to determine the combination of the defined parameters that best satisfy your set goal. This is pretty incredible as it cuts down on the number of iterations that you need to refine your design, greatly improving your productivity. ANSYS also have a similar tool that take this one step further, which is called topology optimization. In this, you can set similar constraints and goals, but instead of specifying parameters, what you do is you input a vastly excessive design. And through various rounds of FEA analysis, it will automatically remove material in strategic areas to meet your set goal. In this example, we have a topology optimized work stool, and you can say we started off as a big cube, and we specified we only wanted 10% of the material to remain, and we wanted to sustain these loads with this factor of safety. And this was the final shape that it came up with. Now there are many downsides to that, and the major one is apparent in this photo right here, and that is manufacturability. An annoying trend is that highly optimized designs are often not manufacturable through conventional methods. The team is still learning some of the manufacturability constraints that you can add to your simulation, and are also trying to manufacture more components through additive methods that can actually make these organic-looking designs. However, if nothing else, topology optimization allows you to find the theoretical best-case shape, which you can then use as inspiration and edit to make manufacturable. The second really important simulation type I want to talk about is Computational Fluid Dynamics, referred to as CFD. Aerodynamics is such an important part of a solar car's performance, estimated to make up close to 70% of its power losses. However, there are many intuitive ways to design an aerobody that is aerodynamically efficient. This includes reducing the frontal area, reducing the number of and the harshness of junctions in the body, ending all components in sharp trailing edges, and trying to follow efficient 2D profiles as much as possible. However, intuition can once again only get you so far. To continue optimizing any further from a rough concept, you need to have a way of knowing for certain how the air is behaving around the car. For many applications, this step would be done using a wind tunnel. However, this is simply too expensive for the team to reasonably achieve. Instead, we use what is essentially a virtual wind tunnel in the form of a CFD simulation. In this, we start off with the CAD model of the aerobody that we want to simulate. The main difference to FEA is that instead of importing the aerobody itself, we import all the air around the aerobody and remove the area where the aerobody was. This is because instead of simulating a car moving through the air, CFD actually looks at wind moving over a stationary car at the same speed. The empty area where the aerobody was acts like a wall that the air can't pass through and hence has to go around. And through this, you can see how it behaves. Once your CAD model is in, we do the meshing process. Now, like I said, I'll dive deeper into meshing later on. But the important thing to know is that a lot of aerodynamic study, the important thing to know about a lot of aerodynamic studies is that a lot of complex interaction occurs very close to the surface of the object in what is called the boundary layer. This is why your mesh also needs to be incredibly fine in the few centimeters directly above the skin of your air body. Once you have a mesh, you can specify your boundary conditions. This includes how the air is entering the wind tunnel and at what speed, how it's exiting the wind tunnel area. You can set your ground to be moving to better simulate the real world. And you can also set your tire surfaces to rotate in order to capture the complex interaction between an exposed tire and the air. Compared to FEA simulation, CFD has many more cells in its mesh, and the mathematical model it needs to solve is also much more complex, leading to many more simulation parameters that you can tune and also much higher simulation times. Fluid mechanics involves nonlinear processes dealing with inherently unstable phenomena such as turbulence, meaning the solutions are not always constant, which means that the calculation iterates until the results start converging onto one. This makes CFD simulations very hard to get right and accurate. Once you do have a good result, what you can do with it is pretty incredible. The main things I use to analyze an aerobody's performance is to look at the various forms of pressure plots to see if there's separation occurring or if unnecessary forces are acting on the body. We can also visualize vortexes and other turbulent flow generated around the car, and quite often can track back to what part of the car is actually generating it. Using this and many more results variables, we can compare iterations of a design and evaluate if the changes made were good. Over many iterations of CAD and CFD, we can end up with a highly optimized solar car that produces very little aerodynamic drag. Now, like I mentioned in the previous slide, a lot of the aerodynamic performance of a solar car revolves around using the right airfoil profiles to construct your 3D geometry. As the bottom image shows, any solar car aerobody consists of various shapes and sizes of airfoils placed at various locations in various orientations across the car. These are joined from one to another using complex surfaces that flow nicely into one another, creating smoother junctions. However, for the final shape to be good, each airfoil needs to be good. For this, we use programs like XFLR5, which is shown in the top image. In this, we can design airfoils that are the appropriate shape to actually cover the insides of the car, like the driver or tires, etc. And then we can tweak these profiles to simulate them to see plots of coefficient of drag, coefficient of lift, and other versus the angle of attack. The best performing ones go into our 3D geometry. Now, the cool bit of the CFD side of things that I want to talk to you about is a tool in ANSYS called Adjoint Solver. Now, this is sort of like topology optimization for CFD. It allows you to import a design and create restrictions like, it can't pass through this area or it can't get any smaller than this size, etc. Then you can set goals like to optimize for the lowest straight line drag force. Using this, it analyzes what areas of the geometry causes the biggest change in the results if changed. It then moves them around slightly to try and improve the design. If a change causes an improvement, it keeps going. And if it doesn't, it goes back and tries something else. In this way, it tries to iterate to find the most optimum aerodynamic shape. Now, this has its limitations. You can't exactly put in a brick and expect to get, a solar car out. The changes it can make are very minute, like tweaking the curvature of various surfaces to try and improve the overall performance. It also works better for internal flows and not external flows like the solar car needs. The compute time for these sorts of simulations are also incredibly high. Think about a single CFD simulations, and this is iterating it. However, we definitely do use it for smaller use cases like optimizing 2D airflow profiles and etc. Now, in both of these analysis types, one very common step was meshing. Both simulations are based on specific mathematical models. FEA, for example, would not provide you with any more information than just solving a three-body diagram if it applied the mathematical model over the entire component, considering it as a single item. However, if that component gets split into thousands of smaller cells that create a mesh of the part, the equations can be applied to each cell individually. A very simplified visualization is that it analyzes the behavior of each cell individually and passes the force onwards to the adjacent cells. One cell's outputs are the next cell's inputs. This way, it analyzes what is happening at thousands of locations within the part, allowing the functionality that it does. The same principle applies for CFD. This makes the mesh itself quite critical to the accuracy of the simulation. There are two main factors of the mesh that need to be considered. One is the quality. In simple terms, you want as uniform of a mesh as possible. You want cells that have very even aspect ratios. You don't want very large cells next to very small ones, rather than slowly transitioning from big to small over many layers. For CFD, like I mentioned, you want very specific boundary layers of cells that is right for the part that you are simulating. The second important thing is the density. The finer of a mesh you have, the more detail you'll be able to see in the results. You'll be able to differentiate the conditions at different locations with more granularity. And you'll be able to capture smaller disturbance. You'll be able to capture disturbances caused by smaller features more easily, especially in CFD. However, there is a compromise in this. The finer you measure, the more computational resources it takes to run the simulation. This is why it is important to perform sensitivity studies. Using one representative part, you can conduct the simulation with various different levels of mesh density. Once the results stop changing too much, you have reached diminishing returns, and that is the level of mesh you should run to get the best results for the least computational resource. This is shown on the graph on the right as the point where the data levels out. Once you know this, all similar parts can be simulated under the same conditions and saves you a lot of time. Now, there is a big divide in the quality of FEA and CFD analysis that can be done. If using bad software with little experience and with terrible meshing, you can get results that are completely irrelevant. However, if done properly, you can get incredibly close to real-world results. This is why almost any race team in the world employs these type of simulations. We ourselves found that in 2019, the theoretical power efficiency of a car estimated through CFD simulations was within 1% of how it performed in the real world. This was incredibly exciting to us and is a statement to how amazing these simulations are. Now, we've discussed what it can do, and I want to talk a little bit more about what it will cost, less in terms of dollars and more in terms of what you'll need to consider. The first consideration is the software costs. There are many different software available with varying functionalities at varying price points. However, any good packages are within the tens of thousands of dollars per year per license, plus what it would cost for it to support. Computing resources are also very important. These simulations are very, very computationally intensive, especially CFD, where the mesh sizes are quite a bit larger. As an example, we were able to run the level of CFD simulation that got to within that 1% of real world for the Solar Car air body, a sim that had approximately 50 million cells in less than 48 hours on a prosumer workstation that was in the ballpark of $4,000. However, this is very scalable. Lesser machines can run it over a longer time, and better equipment could run it within a matter of hours. The type of computing needed would heavily depend on your use case, but it's still an integral cost to consider. Labor is also important, although to us, as a voluntary student-led team, it's not something we think about too much. But using the software is a very highly skillful task, and it often requires extensive and expensive training, which can add up quite significantly. Now, we are proudly supported by the amazing Leap Australia, who are our partner for the Answers package. We are also a very small team that is only building one vehicle every 2 years. However, even if we had to incur all of the software and labor costs involved, we still believe it could be a cost saver for us. We are all students who are still trying to learn engineering design, and we are trying to optimize our design to the absolute leading edge. There is no way we would be comfortable with one of our team members driving such an experimental vehicle without the appropriate validation. Without computational simulations, this would mean we would need to do mechanical testing for every single component before we put it on the road. This would mean testing a lot of parts to destruction. Because we are still students learning, the mistakes we make would only be exposed through physical testing and not through computational simulations, leading to many more manufacturing runs, and it would also drastically lengthen our project timeline. Overall, we believe that this would be less cost-effective than spending the money on computer validation. I do urge you to explore what it can also help you within your business or company. Now, in 2021 and 2023, the regulations are looking to be much more stringent on stability. However, the increased ride height requirements and the introductions of three-wheelers, there's a real ease with which car configurations can become inherently unstable. The regulators will conduct a 45-degree tilt test as a way to verify stability, but within the team, we are looking for further validation. Something that looks at wheelbase, track, the weight distribution, the suspension geometry, shock characteristics, and tire data all together, and something that we can use to simulate various extremes of operational conditions that the car will be under to see how it would react. This is where a multi-body vehicle dynamic simulation can come into play. This is something that the team has never looked into before, but it's looking necessary now more than ever. We are attempting to use Adam's car to create a digital twin of the car that accurately models all of the characteristics listed. From here, we can create various road surface maps and driver input graphs to simulate any common or extreme situations. We hope to be able to simulate hard cornering, braking while cornering, going over cattle grids, and also swerving maneuvers that may be a reaction to crosswinds. Out of this, we hope to be able to see the physical output of how the car behaves, the forces through the suspension components, the reaction forces at every wheel, and many, many other things. Not only will this be able to validate the overall design stability, but it will allow us to optimize the suspension geometry for stability, which before now has just been looked at from a rolling resistance point of view. As of right now, I don't have much more to share about this, but I really hope that we can implement this into our design workflow and that we can share more results soon. So that's the end of my presentation for today. Thank you all so much for listening. I have on this slide the contact details for myself and also for Leap Australia, one of our partners. Please feel free to contact me if you have any more questions regarding what was presented or would like to get involved with the team as a member or a partner. For inquiries about purchasing such software for commercial applications, please do contact Leap. They're incredibly knowledgeable and provide unbelievable support. Now I'll hand over back to Karthik to facilitate the Q&A. Thank you.
Awesome. Thanks for that, Divyam. That was really, really informative about, how we tackle our simulations throughout the team. A couple of questions that we've got through in the chat from the audience. We've got a question which says, how do you ensure that the results you get through these computer simulations reflect in the real world?
No, that is a great question, and it's something that we need to make sure that we're on top of almost all the time. And it's especially hard for things like composite simulations, where it's so dependent on the mathematical model, the material data that you're able to provide to the model, and so forth. So what we try to do is calibrate our analysis using some parts that we test destructively. So if there is a representative component for composites, it could just be something as simple as a composite plate. We're able to test all of our settings for similar analysis on that plate, see what results we get through FEA, and then test that plate to destruction, and then see if the results match up. And that way we can, make changes to our settings and calibrate it to be as accurate as possible, so that we, can get as close to real world as possible. And then obviously we do always have to account for a little bit of a difference, and that's why our factor of safety comes into play. And we use a factor of safety that will cover pretty much any differences there might be in the computational results.
I know you were talking there about those settings and things. One of the other questions we've got is, how do you develop your initial data for those input variables for simulations?
No, that's a great question. So for the case of CFD analysis, our use case is quite simple in that we're going in a very straight line, and the wind where the car is moving at a cruising speed of somewhere in the 90 kilometers an hour. So our wind speed and our ground speed for the simulation is calculated from there. For FEA, it's a lot more difficult, because for the actual by regulations, we've been provided with a few reference numbers for what sort of load suspension systems can expect to be put under, and that's in our regulation. So what we do is set those as the input loads at the wheel. But the issue is, that's fine for full assembly simulations where we're simulating the entire suspension as one, and we can just set the input at the tire. But what if we're, simulating just one other component that's, further up in the assembly? Well, in that sort of cases, we use free body diagrams, and there's various software that can, do this, or, quite often you can do it by hand. But, the force transmitted through each individual part and the reaction forces at where it passes it on to the adjoining parts can be calculated using basic free body diagrams and solving those for reaction forces at each sort of interval. And so if we sort of think about what is the force transmitted from the upright to the lower control arm, we can use the reaction force there as the input for what the lower control arm is actually under. And so that way we're able to calculate each of our forces.
Yeah, that sounds good. Like a lot of maths is involved with that. A bit of a personal question. CFD and FEA look quite complex. How long have you personally been working on it, and how did you get to learn the tips and tricks?
No, that's great. So I've been on the journey to try and learn this sort of stuff for around, I would say, 3 years. It started, I guess, when I was in high school doing F1 at schools, which sort of got me into some very basic CFD analysis, and pretty much, every regular interval of time, you look back and you think about how naive you were in some of the things you were doing 6 months ago, and because you've learned so much. And so my personal experience has just been one of constant learning, and it's so great to have so many great team members and past alumni who've been able to support us through this. We also have Leap Australia, our partner, who are pretty much experts in the thing and are able to provide technical support when we're really stuck on something. And then more than anything, Google is our best friend. Any challenge I have, someone almost certainly has had it before, and just doing the right amount of research, we were able to learn everything. So yeah, it's been a good 2-3 years looking at this sort of stuff, and there's a long way to go.
Yeah, definitely. Following that, do you think your intuition, your personal intuition, has developed, going through these simulations, and I guess there's trials and tribulations with simulations?
I think so, in the sense that often with FEA and CFD, things go wrong. Simulations do not work, or do not get you the results that you were after, in the sense that it doesn't actually calculate your results properly, and it's very hard to diagnose why, and especially when you're starting off, it's very complicated in the diagnosis process of what's going wrong in my simulation, and over time you sort of develop a mental checklist of all of the very, very small things that you are so difficult to pick up that can trigger issues in your simulation. And so those have helped a lot, and now I've been able to see a progress in how often my simulation works on the first go, which is still not that often, but it's more often than it was, I guess, when I was starting. And then the second improvement you can obviously see is where your starting point is for a simulation. Being able to do it so much, your intuitive mind of figuring out or trying to sort of visualize what is the stress distribution in this part going to look like, how is the air going to move around this sort of surface, does improve slightly. And it's not what CFD can tell you, but what that helps with is it allows you to intuitively design something that's a lot closer to optimum. And then with CFD added to the top of that, you can go above and beyond.
Yeah, definitely. Constant learning curve, of course. Another question that we've got in the chat here is a bit more about aerodynamics. It's obviously very critical to the car. Does polishing the paint help? And what sort of considerations do you go through in that painting process for the car to achieve prime aerodynamics?
No, absolutely. That's a great question. So one of the major types of drag, there are a few types that would affect a body moving through the air, but one of the ones is you know, the skin friction caused by air shearing across the surface, and that is a relatively, you know, large contributor to the overall aerodynamic drag of a solar car. And so having a smooth surface finish is very important. But more important than that, honestly, is having smooth transitions between different parts of the car. Now, we have quite a few seams in the car, so you know you want to think about where your array actually seats on the rest of the car, where your canopy seats on the array, your wheel fairing covers and whatnot. Those all create seams, and your aerobody simulations and your CFD analysis are all done assuming that, you know, it's all one continuous body, but obviously it's not. So getting those seams to be as tight as possible to, you know, create that smoothness and not have a jarring sort of junction is very important. Another cool thing we do obviously is a lot of teams, and you know, it would be quite intuitive to do so, is for logos and stuff, you know, putting stickers on the car. But obviously that creates a slight ridge in your surface, and that could be enough to, you know, lose us a bit of performance here and there. And so what we do is actually paint in those logos and stuff into our livery design, and you know, our partner at PPG you know, do an amazing job of painting it in a way that, you know, after the clear coat there's basically no distinguishable sort of you know, bump where we're transferring from you know, the normal red of the car to, you know, sponsor logos or to our you know, team number or whatever. So you know, those little things are pretty cool, but it is quite important to the performance.
Yeah, quite a precision, you know, part of the car that you need to get right. Another question we've got here in the chat is, I know motorsport teams, you know, they use wind tunnels to validate their simulations. How beneficial would a wind tunnel be in our case for our solar cars? And cost aside, do you think it's something worth the money for a team like us?
So I would really love to be able to use and work around a wind tunnel. You know, it's something that would personally really excite me, and you know, just as a point of learning for all of our team members, I think it would be quite invaluable for the team. Now CFD is getting to a point, and I'm not saying that, you know, the team is at that point, but CFD as a whole within the industry is getting at a point where it's, you know, quite indistinguishable from, you know, wind tunnel results, and quite often CFD can be a much quicker, faster alternative to wind tunnel testing, and it's slowly making wind tunnels, you know, less important. They're still important, but you know, less so. And we see that with F1 as well. There's a lot of talks about, due to the budget caps that they're putting from 2022 onwards, they're discussing the actual possibility of stopping teams from using wind tunnels and moving solely to virtual simulation in order to level the playing field with costs. And I think that sort of sets a benchmark as to, you know, how close you can get with CFD to the wind tunnel results. However, you know, there's a bit more of that, you know, tactile element that you don't get, and it is still something that, you know, I would be very excited to be able to explore with the solar car team. And there's not too many options around in Australia, but it would be cool to have that opportunity.
Yeah, I'm with you on the excitement of, you know, hoping maybe one day.
Yeah.
But yeah, we've got two last questions in the chat here. One of them being, do these simulations require constant supervision? And if so, how does, you know, the labor costs factor in?
Right. So quite often the setup can be quite time consuming. Obviously, after your design is done, all of the steps you need to do with transferring your files over, meshing them, setting your boundary conditions, setting your simulation conditions, is quite time consuming. But more often than not, it's for your first simulation that it's quite time consuming. If you're iterating a design, over time, that setup time gets less and less, and then the majority becomes your computational time. And computational time is more or less unsupervised. You know, we at Solica, it's pretty full on. We were able to, set simulations up at, regular intervals throughout the day, just so we can, time it with the rest of the work we have to do. So, that's pretty good. There's obviously always the chance of a simulation failing. And when it does do that, it's good to know earlier rather than later, so as to not waste too much time. And in that sense, some minor supervision or just, looking at the screen every now and then doesn't hurt, but it doesn't require active work.
Yeah, that's good to hear. And our final question, how do you go about verifying that manufactured parts match up with simulations? Maybe if you want to touch on if there's any destructive or non-destructive ways that we go about that.
Yeah, so obviously, I think the first question answered a little bit of this, but we do have one amazing machine at Advanced Manufacturing Precinct at Western Sydney, and that is the Instron fatigue tester. And that, I'm not sure of the exact numbers, but it's able to, apply a very, very high amount of load at very high frequencies. And so you can obviously test the general, destructive testing of, pulling it apart or compressing it. And then you can also test your fatigue loading and cyclical loading and see how it holds up to that. So, there are a few components on the car that are, I guess maybe less easy to get perfect with just CF computational methods, or, sometimes we might have concerns about a part and a lack of confidence in the computational results that we do use the things like the Instron tester to do. One of the components in TED 3 was our suspension mounts. They were actually quite new for the team in the way they were made, because they were actually composite, I would say ears is the best way of describing what the mounts look like. And they were something really, really new for the team. And, there was probably, I guess, just a bit less confidence in just this computational results of, how they were going to perform and how they were going to hold up, because they were so integral to the car being safe. And so being able to Instron test a few of those, and, thankfully we were able to, the team was able to validate that they were more than safe enough. We were able to, use that machine to just double check some of the stuff.
Yeah, awesome. Well, thanks for that really informative session there, Divyam, about computer simulations and what we do as a team. Like always, you're welcome to join us throughout the day for more. We've got another technical presentation coming up in a current partners session where you'll hear from our partners and, about how they support us very soon in about 15 minutes. If you do have any other questions or anything you'd like to talk about, contact Divyam about FEA or anything like that, or Leap Australia, scan the QR code and their details will be there. Other than that, thanks everyone for coming and have a great rest of the day. Hope to see you soon.
Thank you, everyone.
Thanks, everyone.